Hey everyone, we're back at it again looking at section 6.7. Now we're looking at financial models, which are applications of exponential and logarithmic functions. I'm just kind of finishing off that chapter. And so we're going to deal with interest rates today. Very practical application. Obviously you see interest rates anytime that you invest money in a bank, like a savings account or a CD or any other sorts of investments. The interest is the amount of money that you make by investing your money. Okay, it's usually a percentage of the amount that you invest, and it also increases the longer you leave it there, leave the money there. So that's you get a factor of time involved. Okay, you can also pay interest if you are taking money out or borrowing money from a bank. Okay, so interest is typically either earned when you invest or paid when you borrow. All right, a very simple way to calculate interest is called the simple interest formula. I equals PRT. I'm sure you guys have seen this before. I is the interest rate, I is the amount of the interest that you earn. P is the principal, that's how much you actually invested or borrowed initially. R is the annual rate in decimal form, even though it will usually be given to us as a percent. And then T is the amount of time in years. And so when you put these together, you take the amount that you invest, multiply it by your rate. That'll give you the interest for a year. But then for every year that you have it invested, it grows more. So you also multiply it by the amount of time. Okay, so after 2 years you'd have twice as much interest, and so forth. Okay, so now what we're really going to focus on today is not simple interest, but compound interest. Compound interest is this idea that periodically, if you're investing in a bank, the bank will calculate your interest and put it back into your account so you can earn interest on not only the original principal but also the interest from the previous periods. Then the next period you earn interest on that previous interest, and so forth. And so the interest builds a little bit faster. It's a little bit more of an incentive to invest there. It's also important when you take out money. All right, or when you borrow money, you pay interest on a compounding schedule as well, because then when you pay in, the bank gets a little bit more interest every month because your interest is compounding. You're paying interest on the interest and so forth. Okay, so these things compound. The compound interest formula that we're going to use, and I won't go through and derive the whole formula for you. Actually, before I write out the formula, the derivation of it, the proof of it, is in your textbook on page 469. You can see it right here. I'm not going to go through the whole thing just to keep this video relatively short, but you can read through it if you like. It's not terribly complicated, but if you're interested. The final compound interest formula is A equals P times 1 plus R over N raised to the NT power. Let me explain where some of this comes from so it's not completely strange and foreign looking. First of all, I got to define the new variables. Any variables that repeat are defined the same. The principal, the rate, and the time are the same. The A, however, is the final amount. So A is the final amount. So that includes the principal and all other interest. The N is the number of compounds per year. Okay, the number of compounds per year. That's the number of times the bank would be putting money back into your account every year, calculating the interest. And so where this formula comes from if you think about the original formula being the principal times the rate now is a weird base, right? It's a base with an exponent. Now this base has a 1 plus something. The 1 is the original principal. Remember, the final amount includes the original principal and the new interest. The 1 gives you the original principal. The rate here, the r over n, this is your rate times the principal, which would generally give you the interest, right? That would be your rate times principal. However, when you divide it by n, that gives you the portion of the rate each compounding period. For instance, if you were compounding monthly, the bank would not want to give you the full interest rate every month. It would give you 1/12 of the interest rate every month. So you divide by the 12 there, whatever the number of compounds is. Okay, and so you add those two together, the original plus the interest, and you get the final amount in the account. Now the exponent comes in because you're doing this every time there's a compounding period. So n times t, the number of compounds per year times the number of years, is the total number of compounds. And so that tells you how many factors of this thing need to be included in order to accurately calculate the final amount. So if you had 60, if there were 60 compounds, maybe it was 15 compounds per year for 4 years or something, then you'd have 60 factors of this multiplying the principal. Okay, so we need to raise it to that power. Alright, so that's just an overview of where everything comes from. Again, the full derivation is in your textbook. Now what I want to do is go through a couple examples, and just so you can see kind of how to use this formula. If I were to invest, let's say, a principal of $5,000 at an annual interest rate of 2% for 3 years. Okay, let's say I just started off with those 3 pieces of information. That gives me everything in the formula except the n and the a, the 2 new pieces of information. Now I'm going to show you an example, or calculate this with different compoundings, just so you can see how they compare. So let's take a look at, let's set up a little table here. Let's take the compounds. How it compounds, I should say. And so let's say we were to compound this annually. Oops, U-A-L-L-Y. Alright, then that would mean the n value is equal to 1. Now I'm going to fill in a table here, just kind of make this with different types of compounding. And so if we were to compound semi-annually, it looks like an M, that's 2 n's there. That would be twice a year, right? Once every half year is semi-annually. Quarterly is a common compounding, that is 4 times per year, that's every 3 months. Monthly, well, there's 12 months in a year, so that'd be 12 times. Weekly, if you were compounding weekly, well, there's 52 weeks in a year, so that would be 52. Daily, well, generally there's 365 days in a year, unless it's a leap year. But generally banks will use 360 here, just because 360 is a really nice number to calculate things with. Hourly, so we could go even more than once a day. We could go hourly. All you'd have to do is take 365 and multiply it by 24, and you should get 8,760. And if you wanted to do this minutely, that would be every minute. Take that previous number, multiply it by 60, and you should get 525,600. Double check and make sure those are right. 365 times 24, 8760. Multiply that by 60, and yeah, those look good. And then secondly, if you were to go every second, you take that number and multiply it by 60, you get 31,536,000. Big numbers there at the bottom. And you could even go more than that. You could compound this every nanosecond if you wanted to, or whatever, some super tiny fraction of time, and get a really big n value there. But what's interesting is as the n value increases in the formula, your denominator gets bigger, which makes this number smaller. The base gets really small, but the power gets really big, and so they're kind of counterbalancing. Okay, this number gets small, the fraction does, but the power gets big. All right, I'm going to go through the actual, fill in the actual table here with all these values in the next video.